Hello everyone. In this video, we are pleased to introduce our work, X-Adv, Physical Adversarial Object Attacks Against X-ray Prohibited Item Detection. Deep learning has been introduced into safety-critical scenarios such as X-ray security inspection in public transportation hubs such as airports. In this scenario, deep learning-based detectors are utilized to assist inspectors in identifying both the presence and location of prohibited items during X-ray scanning. Specifically, the object detector F-theta takes an X-ray image I as input and outputs key detection boxes with locations B key and confidences C key. This approach significantly reduces the amount of human labor required and helps to protect the public from severe risks. Despite their promising performance, DNNs are vulnerable to adversarial examples. Adversarial perturbations are imperceptible to humans, but can easily lead deep neural networks to make wrong predictions. When performing in the physical world, those perturbation-based attacks are vulnerable to physical changes, while an adversarial patch has a much higher application value in the real world due to its strong resistance to physical influences. In this paper, we take the first step in physical world adversarial attacks on the X-ray prohibited item detection scenario to deceive the detector to wrong predictions by strategically placing adversarial objects around the prohibited item. However, simply extending existing physical attacks that work well on natural images to the context of X-ray images is non-trivial, owing to two main challenges. The first is the different imaging principles. For instance, the wavelengths of X-rays and visible lights have a huge difference, and the X-ray imaging pipeline is confidential. The second challenge is the complex overlap. Luggage passed through an X-ray scanner often contains a large number of objects made of different materials, and overlap between these objects can degrade the attack performance. To address the above problems, this paper proposes an adversarial attack approach called X-Adv to generate physically realizable adversarial attacks for X-ray prohibited item detection. We generate physically realizable 3D objects with adversarial shapes. To resolve the difference in imaging principles, we propose the adversarial shape polishment to derive a differentiable converter that projects 3D objects into X-ray images, so that we could update the shape of the object using the gradients of a surrogate white box detector. As for the complex overlap, we propose attacking location reinforcement to find the locations that achieve strong attack ability even when occluded by other objects, and ensure that the placed adversarial objects do not overlap with the prohibited item. In summary, our X-Adv can generate adversarial objects by jointly optimizing the shapes and locations for X-ray attacks. To be more practical, the adversarial shape polishment simulates the X-ray projection pipeline from 3D objects to 2D X-ray images in order to perform gradient-based attacks. We here first revisit the attenuation rule of X-ray photon beams. When the same photon beam passes through a certain absorber of finite thickness X, the attenuated intensity I is given by this formulation. We assume the transformation from intensity I to the color G is a linear transformation, and therefore we can use the following exponential function to formulate the process. When it comes to the attacking location reinforcement, due to the fact that the cost function is not differentiable to the location of adversarial objects, we inspired by the reinforced algorithm and introduced gradients between attack locations and the cost function. Specifically, we first define an available attacking area where we can place our adversarial objects and divide it into evenly spaced grids. Each grid can be denoted by an action sampled from a policy network pi. As a result, the gradient of the objective function JW with respect to W is shown as this formulation. G refers to the reward of the policy, which consists of two terms, the attacking performance L classification and the standard variance of the locations of adversarial objects. The standard variance guarantees each adversarial object to become dispersed, which is easier to implement in the physical world. We conduct extensive experiments to evaluate the performance of X-Adv. We choose two high-resolution X-ray datasets for prohibited item detection, Op-X-ray and Hi-X-ray. Images from these datasets are captured and gathered from realistic sources, which contain diverse suitcases of different sizes and shapes, and the prohibited items are surrounded randomly by other items of different materials. To verify the effectiveness of our attacks, we apply faster RCNN and two SSD-based models designed for X-ray prohibited item detection. The metric of our experiment is mean average precision, which is most widely used in object detection tasks. The MAP value depicts the overall performance according to precision and recall values. We first conduct experiments in digital world under white box settings. From the results, we observe that despite having eliminated most of the colors and textures in the X-ray images, the adversarial attacks still pose challenges in the X-ray prohibited item detection scenario. It should be noted that X-Adv seem to fail in some categories of X-ray, such as laptops. We hypothesize that the reason lies in the characteristic of the target object. Laptops usually occupy large proportions of an image, while our patch is much smaller than these objects. Then, we further investigate the X-ray prohibited item detection model robustness in the physical world setting. We first illustrate the attack pipeline for our physical world attack. We first generate adversarial object using our X-Adv based on the white box pre-trained target model. We then transform the adversarial objects from 3D mesh format into STL format so that we can use a third-party 3D printer to print this 3D object in metal. We then put our adversarial objects into the fabric plastic box with other items and employ several workers to scan them into X-ray images using a commercial X-ray scanner. Finally, we test our physical world adversarial X-ray images on black box X-ray prohibited item detection models. From the table, we can conclude that the physical attacking ability of X-Adv has a significant impact on detection performance. We also provide some detection results of some X-ray images in our physical world experiments. Next, we investigate the key factors that might have impacts on the attackability of our X-Adv, thereby providing comprehensive insights and promoting a deeper understanding of our strategy. In brief, we conduct thorough ablations on several factors, such as attack locations and number of objects. We then analyze the attacking performance of different materials of adversarial objects and the distribution of TP and FP bounding boxes. Moreover, we discuss some countermeasures against X-Adv. We propose 3 possible defenses and evaluate our X-Adv against them. Data augmentation introduces additional adversarial object-like patches into the original images, and we find it can improve the robustness of detection models. Adversarial detection aims at detecting the existence of adversarial examples. We build a binary classifier to distinguish the benign examples and the adversarial examples, while it cannot reach a high accuracy. Adversarial training is the most widely used defense method, while the PGD adversarial training cannot defend against X-Adv due to the difference between perturbations and patch attacks. Adversarial training with X-Adv could mitigate the attack to a certain extent. Finally, we believe a dataset can be beneficial for boosting research. Thus, we present a physical world X-ray inspection security robustness evaluation dataset called X-Adv. We collect data from an advanced X-ray security inspection machine and select 4 categories of prohibited items that frequently appeared in daily life. As an adversarial dataset, the X-Adv dataset have 5 different severity levels, which contain 0 to 4 adversarial objects. We further evaluate the detection performance on X-Adv, and the result is listed in the table. Okay, thanks for your watching. For more details, please visit our code page.